Welcome to my lecture on the ratio test, and I've started writing out what the ratio test is. So the first step in the ratio test is to calculate this limit of the ratio of a sequence of an plus 1 over an. And I'm going to call this limit L. There are three possible outcomes for this limit. So one of three things will happen. If L is less than 1, the series AN is absolutely convergent. If this limit is bigger than 1, the series is divergent. And the series being the summation of an, so maybe I'll write that out. Then the last scenario is that the limit is 1. Okay, and this tells you no information. And in this situation, you need to use another test. And there's a long list of tests for convergence or divergence. There's the integral test, there's the limit comparison, there's the comparison test. There's several others. So if L is equal to 1, no luck. And I want to warn you, people get confused a lot of the times with the statement of the ratio test and the limit comparison test. They both involve limits, but their statements for convergence are different. So don't confuse the two. In the limit comparison, the limit has to be bigger than 0, otherwise there's no information. Okay, so let's use this test. Okay, and I'm going to consider an example here. Okay, and we'll do two examples, in fact. Is this series convergent or divergent? And we'll use the ratio test. So we'll use this ratio test with a sub n equal to n over 5 to the n. I'm going to compute this limit of a sub n plus 1 over a sub n. Okay. One remark on outcome 2 here, if the limit's infinite, that's still bigger than 1, just FYI. Okay. So I'm going to have n plus 1 over 5 to the n plus 1 divided by n over 5 to the n. We're going to simplify this by inverting and multiplying. Okay, I get to cancel that 5 to the n with the exponent there, and I'm left with this limit as n goes to infinity of 1/5 times by n plus 1 over n. And using calculus here, we see that this limit is 1, so this is 1/5, and that this is less than 1. So this is the limit L here, and it's less than 1. So we refer back up here, and we go to case 1, where the limit is less than 1, and our conclusion is the series of n over 5 to the n is absolutely convergent. Since L is equal to 1/5, and that's less than 1. Okay, so we got an example of convergence. Let's do another example. Is the series of n factorial over 3 to the n, is this convergent or divergent? Okay, well, we're going to answer this using the ratio test. And here a sub n is going to be this n factorial over 3 to the n. I need to compute this limit as n goes to infinity of an plus 1 over a sub n. Okay. So we're going to compute this limit of n plus 1 factorial divided by 3 to the n divided by n factorial, and I apologize, in the numerator here that's 3 to the n plus 1 over 3 to the n in the denominator here. So everything's positive, so I drop the absolute value. I'm going to get this limit n goes to infinity of n plus 1 factorial over 3 to the n plus 1 multiplied by 3 to the n over n factorial. Okay, cancel the 3 to the n with that n, and I'm left with this limit. Limit as n goes to infinity of 1/3, and in the numerator here, n plus 1 factorial just means I take n plus 1, I multiply it by every term less than it, so the first one less than it is n, then I multiply it by n minus 1, and I keep multiplying it until I get down to 1. For n factorial, that starts at n, I multiply by n minus 1, I keep multiplying by everything less than n until I get down to 1. We see that these terms right here, they all cancel. And I'm left with this limit as n goes to infinity of n plus 1 divided by 3. This keeps getting bigger and bigger, so it limits to infinity. And since this is, we need to go back to our cases. Since this is bigger than 1, it falls in case 2 here. Okay, bigger than 1, so divergent. Okay, so the series is divergent by the ratio test. Okay, so now that we've done the ratio test, you might be curious, like, how does it work? And so I'm going to outline a proof of part 1. Okay. Okay, so one thing that I'm going to say is that by the monotonic sequence theorem, it is sufficient to show that the series is bounded. Okay. So that's what we're going to do. We're going to prove that it's bounded. Okay. Well, the fact that this limit as n goes to infinity of an plus 1 over a sub n in absolute value is equal to L, and L is less than 1. Well, this implies, okay, that a sub n plus 1 is less than L times by a sub n. And without loss of generality, we can assume each of these terms are positive. Okay. This implies that this statement is true, and this statement is true for every value of n. That is large, because the limit means that as n gets bigger and bigger, okay, excuse me, I shouldn't have used the L here. I'm going to choose this to be R, okay, R times a sub n, okay, where L is less than R is less than 1, okay. So as n gets bigger and bigger, this ratio gets closer and closer to L. Well, I'm going to choose a value just a little bit bigger than L, but less than 1. Then when n is sufficiently large, when n is large, I get this property that a sub n plus 1 is less than R times a sub n. Well, this means that a of n plus 2 is also less than R times by a sub n plus 1. Okay, but remember, a sub n plus 1 is less than R times a sub n, so this is less than R multiplied by R times by a sub n, and this is R squared multiplied by a sub n. Okay, I can play this game again, and using this logic, this implies that a of n plus 3 is then less than R cubed multiplied by a sub n. Okay, a sub n plus 4 is less than R to the 4th times by a sub n, etc. And this relationship keeps being held. So let's just put this together. If I have this series, this sum from n equals 1 to infinity of a sub n, just writing out the first few terms, I'll get a1 plus a2 plus a sub n minus 1 plus a sub n plus a sub 2, a sub n plus 1 plus a sub n plus 2, and so on. But this is less than or equal to a sub 1 plus a sub n minus 1 minus 1. Okay, then this is where I use this fact above and the geometric series. So now this is less than or equal to a sub n, okay, but a sub n plus 1 is less than a sub n times by r. The next term, a sub n plus 2, is less than a sub n times by r squared, and so on. This part's geometric, and this part is finite. So this is going to be less than or equal to this finite number, a1, plus a sub n minus 1, plus a sub n times by 1 plus r squared, and so on. So this is going to be less than or equal to a sub 1 plus a sub n minus 1 times by a sub n times divided by 1 minus r, and that's a plus there. Since this is a finite number, we have shown that summation from n equals 1 to infinity of a sub n is bounded, hence convergent, by the monotonic sequence theorem. Okay, and then we put this word here, QED, meaning that we've demonstrated what we set out to prove. Okay, so this was just a little bit extra as to why it works. What I really want you to take away is, first, the statement of the ratio test. If the ratio is less than 1, the series is absolutely convergent. If L is greater than 1, the series is divergent. And, just to put some redundancy in here, when I'm talking about convergence or divergence, it's of the absolute value. Okay. If L is equal to 1, there's no information. You gotta do something else. You have a whole litany of tests that you can try. Throw the book at it. Okay. Do not confuse this ratio test with the limit comparison test. Okay. Then the second thing I'd like you to take away is to understand these two examples. The example right here, the top one, and this example right here in the bottom one. Once you understand all of that, if you really want to, you can go ahead and study this proof. Okay. Thank you for joining me.